So today in physics what we talked about were two very important coordinate systems that we're going to be using to actually be able to explain measurements, to use the units like we talked about last time. So we have the Cartesian coordinate system and the polar coordinate system, or plane polar coordinate system. The Cartesian coordinate system is the regular old x and y coordinate system, where this is positive x, this is positive y, this is negative y, and that's negative x. And those positive and negatives are actually very important. The polar coordinates instead use a radius, the distance to something, and some angle. So we have x and y, or we have r and theta. So this is very important, where you could define this point here, say this is at 3, and this is at 1, then we can write this point as 3, 1 for x, y. For this one, you'd have to say that it is at, let's call this 5, and this we'll call 35 degrees for r, theta to be 5 and 35 degrees. You can convert between these two things. The way you do that is by drawing triangles and using trigonometry. So you can see how this right here has a triangle where this is some distance along our x-axis, this is some distance along the y-axis, and you can relate those two, and the angle, and that hypotenuse there, to convert everything from one to the other. So, from geometry we know from Pythagoras that if you take one leg of the triangle and square it, and add the other leg of the triangle, which is squared, you end up with the hypotenuse squared. The other thing that lets us relate this with the angle is to remember our trig function relationships, where tangent of theta is equal to y over x, or the opposite side over the adjacent side. The other relationships here would be sine theta, which would be y over the hypotenuse, and cosine theta, which is x over the hypotenuse, in this case. In case you have trouble forgetting which these are, you can always go back to the mnemonic of SOHCAHTOA, which is very handy. This says that sine is the opposite side over the hypotenuse, cosine is the adjacent side over the hypotenuse, and the tangent is the opposite side over the adjacent side, where we're talking about from the perspective of the angle. So here, the angle is drawn here from the positive x-axis, so the opposite side is y, the adjacent side is the x. So you can go back and forth between these two different coordinate systems, which is great for actually being able to define things in 2 dimensions. Now, if we stay in 1 dimension, however, we can start talking about describing motion and bring in the idea of vectors, which we'll also be dealing with eventually in terms of 2 dimensions. We're going to start off with 1 dimension. A vector is something that has both magnitude, or a number, a value, and direction. So we can talk about displacement in terms of vectors, where displacement is how far something has moved from its original space. Delta x, a capital Greek letter delta means change, x for displacement is equal to the final x, final position, minus the initial position. I'm drawing the arrows on top to say that we're talking about a vector, something that actually has a sign, a direction, along with its actual magnitude. So if I say that we're going to be starting at a position of 2.0 meters, and we're going to be ending at a position of 4.0 meters, then our delta x is going to equal 4.0 meters minus 2.0 meters, which is equal to 2.0 meters. But now, let's say that instead of going from here to here, we're going to go from here to negative 4, so that our ending spot over here, call that negative 4, is over there, and so our new delta x is going to be negative 4.0 meters minus 2.0 meters, or minus 6.0 meters. Okay? So the negative is very important. This is the whole vector aspect of it. The negative is very important because it says that you've gone this way in your displacement instead of going this way. This would be a positive displacement. Now, it's important to note that distance is not the same thing as displacement. Distance is a scalar, meaning it has no direction, it's just a number. So the distance from here to here is 6 meters. The displacement has been negative 6 meters. The distance from here to here is 2 meters. The displacement is, technically speaking, positive 2.0 meters. You could write that as plus. It's just usually taken to be understood that that is plus. Also, if you go from here to here, or go this way, or go way up here and come back down, these all have the same displacement, because you've gone from one spot to the exact same spot. They all have two very different distances. They all have very different distances, but they have the same displacement. If you look at the change in displacement with respect to time, how fast something is going, then you can talk about velocity. The average velocity would be the total distance, the total displacement over the total time. And the instantaneous velocity would be in a segment of time where basically that time is small. So we would use the calculus definition of saying that, in that sense, we take the limit as delta t goes to 0 of our displacement over your time. But the vector nature is there from the fact that the displacement is a vector. So we will continue to deal with these ideas in the next class.